Let's talk about periodic signals. Probably a very intuitive statement to most people when we think about periodic signals is a periodic signal is any signal which repeats itself, right? So here are some examples. Here's a sine wave. I'm showing it for 3 periods. Here's a square wave, triangle, and sawtooth. All of these are periodic signals and they go on forever. I'm only showing 3 periods here. This statement here does not really count as a definition because it's sort of vague. And if I give you a signal and want you to calculate its period, this is not going to really help you much. So we need a, a, a more precise and mathematical definition which will actually help us. So let's look at the definition of a continuous time periodic signal. A signal x of t, I'm considering x of t is a continuous time signal. So t here is a real number. So a signal x of t is a periodic signal if there exists a real number capital T greater than 0 such that x of t plus capital T will be equal to x of t for all values of t. Okay, so note that t has to be greater than 0, otherwise this will be true for all signals, so it's not really a definition then. And then note that x repeats itself after every capital T seconds. Let's look at this definition in the context of the example signals we saw. So in this example, let's consider each vertical scale to be 1 second. So I have labeled the x-axis with the appropriate seconds. Okay, so in here, let's say if I start at 0, and then it's clear that the period should be 2 seconds. So if I start at 0, x of 0 should be equal to x of 0 plus 2, which is x of 2, right? So if I start here and I jump advance by capital T seconds, I go to 2, I end up at the same value. So, and it should be the same for all other values. Let's say if I start at 0.5, then I jump capital T, which will be 2.5, and then I get there. So I can also say x of x of 0.5 will be equal to x of 2.5. Similarly, I can start at any other point. Let's say if I start at 0.7 here, then it will be equal to 2.7 right there. Okay, so this t, that is why you have all values of t here. So no matter where you start, if you advance by capital T seconds, you'll end up at the same place or the same value. That's what this definition is saying. This is a good time now to introduce some notation. So I have the same definition for the continuous time periodic signal here. And this another statement is exactly the same, but uses some more notation, and let's talk about that. So here it says a signal x of t is a periodic signal if there exists, right? So in math, we have like a notation for a symbol to say there exists because this phrase comes up so often, it is convenient to use a symbol. So whenever you see a phrase there exists, you can use this symbol here, which means there exists. And we're saying a real number t greater than 0. So what you're saying here is t must be a real number. So in the best, again, if you want to use notations like mathematical symbols to say that, so you say t belongs to this set real numbers, right? So this symbol here it says belongs to, and this basically this means that this says t is in this set of real numbers. Okay, and you're saying such that x, and sometimes you can, for such that people say s full stop t full stop, but that's if you just want to write such that, that's okay. And x of t plus capital T is equal to x of t for all values of t, right? So again, because this phrase comes up so often, there is another symbol for that, and that symbol is here like this. So this means for all values of t. We can be a bit more specific here. Because x of t is a continuous time signal, we know t must be a real number. So we can also specify that in the definition by saying for all t in real numbers, and we can just say that for all t in the set of real numbers. So when that happens, capital T will be the period of that signal. So we can say um, such a capital T will be the period of x of t. Let me make this math. Let's use this definition to find the period of an example signal. So here is the example signal I'm considering. Find the period of the signal. X of t is equal to sine phi pi t. So if capital T is a period, then t has to be greater than 0. It should be a real number. And x of t plus capital T should be equal to x of t for all values of t. This is the definition. Note that x of t is given to us. So I'm just going to use the definition of what the signal which is given to us, and then just going to plug in these values here. So on the left hand side, I should plug in t plus capital T for t, and I get sine phi pi of t plus t will be equal to sine phi pi t, and this should be true for all t. Also note that I'm using another symbol here. This symbol here means implies. So this statement here implies this, and this implies this because of the definition. I can rewrite the same statement, this statement as this statement here. So what I did is I distributed the multiplication of phi pi into the summation, right? So that's why I got this. Many of you may be comfortable with the statement as it is written here, but some of you, it would probably be easier if I make these substitutions here. So I'm saying theta is phi pi small t and phi is phi pi capital T. Then the above statement here can be written as sine theta plus phi is equal to sine theta. Note that for all t now becomes for all theta. So when is this statement true? So if you remember from trig, for any angle theta, sine theta is given as the height divided by the hypotenuse. And for any angle, so 360 degrees angle corresponds to 2 pi radians. So for any angle, if you add 2 pi radians, you come back to the same angle. No matter where you start, if you add 2 pi, you come back to the same angle. That means if you want this left-hand side to be equal to the right-hand side, then this phi has to be either 2 pi or any multiple of 2 pi. So this equation will be true also when phi is actually 0. But if phi is 0, then this capital T will be 0. And if capital T is 0, that will be a contradiction because we said capital T must be greater than 0. So what we are saying is then this phi has to be any multiple of 2 pi but not 0. Let's specify that mathematically. What I'm saying here is phi must be 2 pi times m. Note that m must be an integer, otherwise it's not really a multiple. Let's say if m is 0.5, then 2 pi times 0.5 is not a multiple of 2 pi. So we have to say m must be an integer, and we also said m is not equal to 0. Again, I'm saying implies because this statement here implies this, and I'm not necessarily saying this diagram implies this. I'm saying this statement implies this, and this diagram is just an illustration or my reasoning for why this statement implies this statement. I can substitute phi is equal to phi pi t, and then this equation here would mean that my capital T should be any multiple of 2 pi, but that multiple cannot be 0. So the question started with asking, okay, find the period of this signal. And then what we are saying is any non-zero multiple of 2 over 5 will be a period of that signal. There is one final thing we need to adjust. So in the definition of the period, we are saying capital T must be greater than 0. So that means m not equal to 0 is okay, but not completely sufficient. So what we want to say is m should be, say, greater than 0. Where's my, yep, should be greater than 0 and greater than 0. So now my t will actually be positive. The way we are defining a period currently is for any given signal, there could be infinitely many periods as in this example. So there is another way of maybe cornering down to that just one value, and this is called the fundamental period of a signal. So the fundamental period of a periodic signal is the smallest positive period. So in this case, so any positive multiple of 2 over 5 is a period of the signal, but 2 over 5 will be the fundamental period. Now let's talk about discrete time periodic signals. Let me underline this. Okay, so the definition is very similar to that of continuous time periodic signals, except that x of n now is a discrete time signal. Note the difference in the notation. I'm using square brackets instead of parentheses, and this n must be an integer. Okay, so a signal x of n is a periodic signal if there exists a capital N greater than 0 and n is an integer, such that x of n plus capital N is equal to x of n for all small n in the set of integers. Okay, so again, very similar to definition of a continuous time periodic signal, except that the discrete time periodic signal should repeat after every integer steps. So, and if there is such a capital N, then that such a capital N will be called the period of signal x of n. The definition of fundamental period will remain the same. The smallest positive n, if there exists such a n, that the smallest positive capital N will be the fundamental period of x of n. Now let's use this definition to find the period of an example signal. So here I'm taking a similar example as I used for continuous time signals. Instead of sine phi pi t, I have x of n is sine phi pi n. Using the definition of a periodic signal, I can say if capital N is the period, then n must be positive, n must be an integer, and x of n plus capital N must be equal to x of n for all values of n. Then using similar arguments as before, I get phi pi times capital N should be equal to 2 pi, or integer multiples of 2 pi. This m must be greater than 0, it's an integer, and we have additional constraint now that this capital N must also be an integer. So then that statement implies capital N should be an integer multiple of 2 over 5, and note that n itself must be an integer. So if you apply all these conditions, then we will get that n should be 2, 4, 6, and so on. So that means all integer multiples of 2 are period of this signal x of n. Okay, now if you want to find the fundamental period, then the fundamental period would be the smallest capital N, which will be 2.